Hello everybody, so we continue talking about graphs, and today we're going to talk about we'll start by talking about vertex and edge deletion. So here is the definition. Suppose we have a graph G, vertex set V and edge set E, and let's say we have a vertex V. Then the graph G minus V, so G with V deleted, is obtained from our graph G by removing the vertex and all the edges that are incident with V, so all the edges that go from V. So if we have, and similarly, if we have a subset of vertices, not just one vertex, but maybe several vertices, then we can remove all of them, and as we do, we have to also remove all the vertices, all the edges incident with vertices in S. So that's how we remove vertices and sets of vertices, and then also we can remove edges, and that's actually easier. So when we remove an edge, so G minus E, so then we just simply remove this particular edge E, and that's it. So we don't have to worry about vertices or anything else. And similarly, if we have a set of edges, then we can remove them all. So we got G minus S is going to be the graph obtained from G by removing all the edges in S. So let's consider some simple examples here. So let's say we have this graph. Now, let's say I want to remove vertex 4. So if I want to remove vertex 4, then what do? I need to remove all the edges from 4. So we have two edges that go from 4, and the vertex itself. So that's going to be G without 4. Now if I want to remove two vertices, 1 and 3, now what do? I remove all the edges from these two vertices. So when I'm drawing, it's easier to first remove the edges and then remove the vertices. So I remove all the edges incident to my vertices. I have 3 edges going out of 1, and I have 2 edges going out of 3, and then I also remove the vertices themselves. So that's going to be G without 1 and 3. Now I can also remove an edge, and that's even easier. So I just remove the edge itself. So 1, 3. So this is the edge that connects them, and I just remove it. Or I can remove 3 edges, a set of edges. So here I have 3 edges. So what do I remove? I remove edge 1, 2. I remove the edge 5, 6. It's here, and I remove the edge 2, 4 over here. So that's going to be the resulting graph. All right. So far so good. So here is another definition. The graph is called connected if any two vertices of G can be connected by a path. And if a graph that is not connected is also called disconnected. So now, if we have a disconnected graph, then it's kind of intuitively clear that a disconnected graph actually consists of several connected components. So it's just several pieces, several connected graphs that just put together. But we want to have some formal definitions and formal statements about those. So yes, still kind of informally, we say that the maximal connected piece of a graph is called a connected component. And by maximal here, I mean that it's a piece of the graph such that I cannot make it larger. I cannot add edges, I cannot add vertices. If I add, I cannot add edges at all because without adding vertices here. And if I try to add a vertex, then I cannot I cannot make it connected anymore. So I cannot enlarge it without making it disconnected. So that's called connected component. A kind of more formal definition could be made in the following way. So a connected component of a graph G well, is also a graph G prime such that so the set of vertices V prime is just a subset of the set of vertices V. So we just take some of the vertices and they should satisfy the following conditions. So every two vertices of V prime should be connected by paths in G. So for any two vertices, there should be a path connecting them. And if you have one vertex in V prime and one vertex in the complement, so outside of V prime, so here this notation V minus V prime means that I throw away V prime out of V, so I take the complement. So if I take two such vertices, one in V prime, one outside, then they are not connected by paths. So I cannot get from V to U by a path in G. And finally, so this was about kind of the vertex set of this connected component. And finally, the condition on the edge set is that we simply take all the edges such that which have end vertices in V prime. Note that no edge has one end in V prime and one end outside because of the previous conditions, because this would violate condition 3 clearly. So there are no such edges. So if one of the ends is in V prime, then the other end is also in V prime. So there is no ambiguity about this condition. Okay, so let's consider some simple examples here. So I have two examples. So the first graph is connected. Well, how do we convince ourselves about it? Well, I can draw a path that basically contains all the vertices here. I think I can. Well, I certainly can draw a walk like that, but I actually can draw a path as well. So if I go like this, then like this, then like this, then like this, and like this. So this is a path that actually contains all the vertices. And therefore, just going along this path, this particular path, we can get from any vertex to any other vertex. So therefore, it is clearly connected. Actually, it's not that hard. If there are not too many edges, it's not that hard to visualize, to just see that which graph is connected and which is not. So the second example, so here it is clearly disconnected. And the connected components are as follows. So these three vertices and the edges connecting them as one connected component, and the other connected component is, of course, well, the rest. So this foregone here. So you can see that clearly in each of the connected components we can reach we can go from any vertex to any other vertex, but we cannot get from one connected component to another. So it's a kind of important to notice that well, on our picture, on our diagram of the graph, some of the edges intersect, but that's just a feature of our diagram, not of the graph itself. So the graph itself doesn't really know that there is this intersection of edges. So this intersection of edges doesn't really mean anything for the graph. So we cannot, in particular, we cannot turn at this intersection. So this graph is disconnected and has two connected components. Well, in fact, we have this little lemma, which is very clear intuitively once again, but nonetheless, I'll have a proof because I like formal proofs. So the lemma says that one can always subdivide the graph into connected components, and that's actually done in a unique way. So it kind of if graph is disconnected, it kind of naturally falls apart into these connected components. More precisely, what happens is that we can partition the vertex set and partition into k parts, and partition the edge set into k parts, so that if you take v1, e1, that's a connected component, v2, e2 is a connected component, and so on. So we've got k connected components. So here this notation, this square kind of cup notation, means disjoint union. So let's say if I have S1 disjoint union S2, so this is called disjoint union. So what that means is that, well, first of all, we do take the union of these two sets, but we also state that their intersection is empty. There is nothing in the intersection. And this sign is for empty set. So this, so for the usual union, I just I just use the usual, or just a sign like that. So this is usual union, just union. So that's just union of two sets. But if we have, if we want to emphasize that the two sets are disjoint, so they don't have any intersection, then we can write this square union. So that's called disjoint union. All right, so do we have this subdivision such that each pair is a connected component of G, and the statement of the lemma is that this is clearly this can be done in only one way. So there is only one way to do that. And well, in the example, and just from our intuition, we clearly see, I mean, that's very natural statement. So, but well, let's do a formal proof here. I kind of wrote it in maybe with too many details even, but let's kind of try to see how one can prove it formally. So what we'll do induction once again. Induction in the order of G, so in the number of vertices of G. Remember that the order is the number of vertices. So the base case is very easy. Of course, if the order is equal to 1, if there is just one vertex, well, it's clearly connected, and the subdivision, well, there is not much you can do for the subdivision. It's just one vertex itself. So there is nothing much to subdivide, so subdivision is trivial and unique. Now we need to prove the step, the inductive step. So what do? We make the assumption, so suppose that for all graphs of order less or equal than n, we already proved the theorem. Now let's say we have a graph which has order n plus 1, so we have n plus 1 vertices. Well, let's take some vertex, any vertex actually, in V. And what I want to do, I want to just take the connected component that contains V. So how do I construct this connected component? I just say that, well, let's take V1 to be the set of vertices that can be reached from V by a path. So we take all the vertices that are connected to V by a path. And then we take E1 to be just all the edges with n vertices in V1. Note once again that no edge can go from V1 to the outside of V1, because that would contradict our construction of V1, because the other end would also be reachable then from V by a path, and therefore it would have to belong to V1 as well. So we just take, there is no ambiguity here, we take all the edges connecting vertices in V1, and just by construction and by definition of, by definition of a connected component, this V1 E1 is a connected component of G. So that's and moreover, we can see clearly that in any subdivision into connected components, the component containing V will have to coincide with V1, V1. So because we'll have to take all the edges, all the vertices that we can reach from V by a path, and that's V1, and we'll have to take all the edges with endpoints in V1. So there is no choices there. And finally, if you consider the complement, so we take complement in the set of vertices, complement to V1 in the set of vertices, complement to E1 in the set of edges. That's again a graph, because all these edges in the complement are going to connect vertices in the complement. They cannot go from outside of V1 to V1, as we noticed before. So that's a graph again. And moreover, since V1 was not empty, it at least contained V small, right? So the vertex we started from. This new graph is of order less or equal than n. So we can apply the inductive assumption, which says that this graph can be subdivided, can be subdivided into connected components, and only in a unique way. So we just subdivide, and we add our first component, and we get a subdivision. And again, it is a unique subdivision, because this component V1, E1, every subdivision will have to contain that, and then the rest will has a unique subdivision by inductive assumption. So that's our proof. So you see, I mean, intuitively it was very clear, but we want to be able to present something very rigorous as a proof here. And induction is a good way to do that. All right, let's go on. Definition. A vertex V is called a cut vertex if by removing this vertex from the graph, we obtain a graph with more components than G. So for example, in this example, V is a cut vertex. Because if we remove it, then the graph, so this graph is connected, but if we remove it, it is not connected anymore. So it falls apart into two components. So let's see if I take a copy, and now I just remove V, so I have to remove all the edges from V, and then V itself. So that's what is left, and that's clearly disconnected. So it was connected before. So this was, say, graph G. It was connected, so just one connected component, therefore. And now this is G without the vertex V, and it is clearly disconnected. And it has two connected components. All right. So similarly, a subset in the vertex set. So here we just had one vertex, and we removed it, and it became disconnected. So more generally, we say that a subset in the vertex set is called vertex cut set if the difference, if after removing all these vertices, number of connected components get bigger. Once again, we get more connected components. Okay. The next definition is the connectivity of a graph is just the size. So that basically it's the smallest positive integer such that there exists a cut set of size of that size. So, and this is kappa. So this letter is kappa. So this is kappa of G. So the kappa of G is the size of the smallest vertex cut set for G. So yeah, this is for a connected graph. And for a disconnected graph, we just said that kappa is 0, because basically for a disconnected graph, we don't have to remove anything. It's already disconnected. So there is one more special case here. So yes, one special case was a disconnected graph. So we just said that connectivity is 0, but there is one more special case. So namely the complete graph. So complete graph is a graph that where every two vertices are connected by an edge. So every two vertices are adjacent. We just put in all the possible edges there. And the point is that for a complete graph, there are no vertex cut sets at all. So because we remove any subset of vertices, still the remaining vertices are going to be connected. And note that this is only true for a complete graph, because if the graph is not complete, that means that there exist two vertices that are not adjacent. And if we remove all the other vertices, so that all vertices except for these two, then it will become disconnected. So clearly we do have cut sets. So unless the graph is complete, we do have cut sets. But for a complete graph, this definition of connectivity doesn't really work, because we just don't have any cut sets. So we extend our definition by just saying that for a complete graph, the connectivity for a complete graph of order n, so with n vertices, the connectivity is equal to n minus 1. So we just define it that way. Note that for a non-complete graph of order n, the connectivity is always less than n minus 1. Because once again, if we leave two non-adjacent vertices and remove everything else, well, it becomes disconnected. So therefore, connectivity is less or equal than n minus 2. So it's less than n minus 1. So if the connectivity is equal to n minus 1, that means that we have a complete graph. So we also say that the graph is k connected if k is less or equal than kappa of G. So basically that means that if we remove less than k vertices, then the graph will still be connected. All right, let's consider some examples. So first, kind of general kind of examples, but kind of simple. So connected, saying connected is the same as saying that kappa is greater than 0, right? Because the way we define things, we set kappa equal to 0 only for disconnected graphs. So that's just by definition. And therefore, connected means that it is one connected, right? Because since kappa is greater than 0, that also that implies that 1 is less than kappa, less or equal than kappa. Therefore, our graph is one connected. All right, and these three things are just equivalent: connected, one connected, and kappa is greater than 0. Now, kappa is greater or equal than 2. Well, it is equivalent to saying 2 connected, and it is also equivalent to saying that it is connected and there are no cut vertices, right? So the cut vertex would be is also a cut vertex set containing just one vertex. So if there is a cut vertex, that means that it is just one connected and not two connected. Well, let's consider some concrete examples. So this is the same graph we had before. Now, you can check that there are no cut vertices here. So, no cut vertices. Well, let's check actually. So let's just try to remove them by one. So if we remove vertex 1, we get this, and that's clearly connected. So 1 is not a cut vertex. If we remove 2, still connected. So 2 is not a cut vertex. Let's try to remove 3. Well, that is connected as well. 4, connected. 5, connected. And finally, if we remove 6, well, still connected. Now, okay, so no cut vertices, so kappa, so that it follows then that the kappa is greater than 1, so at least 2, so it is 2 connected. 2 connected. So the question is, is there a cut set consisting of just 2 vertices? Well, in fact, yes, and there is an easy way to find it. So we do have a vertex of order 2. So a vertex with just 2 edges. So then if we remove the neighbors of this vertex, the graph will become disconnected. So for example, vertex 6 has just 2 neighbors, so it has degree 2. Yeah, degree, not order, degree 2, right? So only 2 neighbors. So if we remove them, the graph will become disconnected, because the vertex 6 is not going to be connected to anything anymore. So this is a disconnected graph, because 6 now is not connected to anything. So maybe, yeah, let me actually make a copy. And oops, what am I doing? Okay. Copy, and so if we remove 5, vertices 1 and 5, so we take G and we remove vertices 1 and 5, then what we obtain is a disconnected graph. So that's disconnected. So one of the connected components here is kind of silly, so it just contains 1 vertex, but that's fine. So that's also a graph just with 1 vertex. So we see that it is not 3 connected, right? So kappa, so the smallest set we can remove to make it disconnected contains 2 vertices. So that means that kappa is equal to 2. So it is 2 connected, but not 3 connected. All right. So that's our example, and that's all I wanted to tell you in this video.